Welcome everyone. So in this video, we are going to introduce the concept of a bivariate joint density function. And so really what we're thinking about this as being useful for is if instead of having just one thing that's random, which we've dealt with for the past month or so, now we might consider having two different random variables that we want to model together. And so I'm in our note packet, I'm on page 4, and there is a definition of a multivariate random variable that's a little bit more general than what we'll mostly be working with, but we'll just briefly mention that the stuff that we do with bivariate random variables can be extended to include more than two variables. You just lose some of the visualization, which is nice when we're first learning. So jumping right in, our definition of a joint density function is given here. And really what we are focusing on with these joint density functions is we're focusing now pretty much exclusively on continuous random variables. And so there's I guess, corresponding functions for bivariate discrete random variables and a discrete and a continuous random variable. But for this class, we're pretty much going to focus on just joint densities of continuous random variables. And you'll notice a couple of properties. So you'll notice that the bivariate density has to be greater than or equal to 0, so it can't be negative, just like a univariate density also could not be negative. And you'll notice that the integration of this joint density across all values of x and across all values of y has to be equal to 1. That's also analogous to what we saw in the univariate case, but we were only integrating over one variable. This is also where we will need, as you all know, there is a Calc 3 prerequisite for this course, and a big reason why that exists is so that you are already familiar with double integrals. So essentially, a quick review, this first integral matches with the dx, and then this outside one matches with, dy. Okay, so that's a little bit of an introduction. As usual, I think it's easiest to see some of this jumping straight into an example. And so we've got this joint density fxy, and we have a definition for that that's given in this little equation. And something that we are now going to pay a lot more attention to. We paid attention to it before, but now we're really going to pay attention to it, is where this joint density is defined. In other words, what its support set is. So where the density is non-zero. If we're trying to visualize what this joint density looks like, it is really that can be done with a three-dimensional plot. And we're in the same place in Canvas where you clicked on the link to this video. I also put a link to another file that has a three-dimensional plot. And I'd like you to pause the video now and click on that file and mess around with that little 3D plot to give you an idea of what this joint density looks like. Okay, did you pause the video? Don't you freaking lie to me. So hopefully you actually went in and messed around with that little 3D plot. On my end, I will scroll down to the 2D version of that. And so again, what this shows is our support. So x goes from 0 to 1, y goes from 0 to 1. And then the 2D version has the density, it uses color to show the density. And so we see that x and y are more dense in the upper right and less dense in the lower left. And so we'll use these little visualizations from time to time just to get a feel for what these joint densities look like. Tackling a problem now, we're tasked with finding the probability that x is less than or equal to 6 and y is less than or equal to 0.33. And so how I'm going to encourage you to approach these problems is to sketch the support set. We're about to do kind of the simplest possible version of this type of problem, and so sketching the support set will definitely come in more handy as we get to more complicated supports. But I'm going to do that for this problem anyway, and so our support set here is just a rectangle. So x can go from 0 to 1, y can go from 0 to 1, and so I've sketched our support set for this particular example. And unless you're really, 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 really talented, you're not going to be able to sketch the joint density in 3 dimensions. And so as far as we could pretty much only sketch the support set, again, unless you're really, really talented with sketching. And so the other thing that we're going to shade is what we're trying to, the volume that we're trying to integrate under to get this probability. And so we're trying to find the probability that x is less than 0.6 and that y is less than 0.33. So I've marked those on the graph, and the area that we're really interested in computing under that 3-dimensional curve is the area that I've just shaded. Okay, so I think for these problems, usually that's the hardest part. Once you actually sketch the support set and shade in the area that you are trying to integrate over, setting up the integral I think is usually a little bit easier. And so you can integrate with respect to x or y first, it doesn't matter. I'm going to integrate with respect to x first. So my first integral goes from 0 to 0.6, and that's with respect to x, and then I'm going to integrate with respect to y from 0 to 0.3. For these problems, I will almost exclusively use ChatGPT. So this one's not really that bad to integrate by hand, and you should have the tools to do so from Calc 3, but alas, I guess I'm a little bit lazy. And I've already plugged into ChatGPT a prompt. And so I'll show you my prompt. So I said, integrate for xy from 0 to 0.6 with respect to x, and then from 0 to 0.3 with respect to y. So I kind of like using ChatGPT both because I think it forces you to be a little bit careful with your language. So you have to, tell ChatGPT what you want to integrate with respect to first, and then what you want to integrate with respect to second. ChatGPT does all of this work, blah, 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 and it gives you a number at the bottom of 0.0324. Interestingly, when I plugged that same prompt in on my laptop, it didn't actually show work. Instead, it showed Python code to compute this integral. And so I'm not sure why it changed, but when I switched over to my iPad to type that in, then it showed the more traditional mathematical formula. So I'm mentioning that just so that you're not surprised if ChatGPT gives you some Python code to compute that integral. We're going to do one more example. And so we are going to find the probability, say that x is bigger than 0.2 and y is less than 0.5. And again, I'm going to use the same strategy. So I'm going to sketch my support set first. So the support set doesn't change. X and y both go from 0 to 1 still. But the area that I'm integrating over does change. So x bigger than 0.2, y less than 0.5. That is going to be this area that I've just shaded in there. I'm going to set up my double integral again. And just to show something different, I'm going to integrate with respect to y first. There will be times in class that we'll see that it'll be easier to integrate with respect to one over the other first, but it does not really matter for a final answer. So I'm going to do 0 to 0.5 for xy dy. And then x is second, so x, I want to integrate from 0.2 up to 1 dx. Again, I'm going to use ChatGPT to compute this, and I've already done so. And you wind up with 0.24. So you could ask yourself a quick question as we're wrapping up. Why is this probability so much larger than the one that we got in the first example? When we're kind of integrating, at least over the support, has roughly the same area. So in my sketches, the support that we're integrating over is roughly the same area. So why is one number so much larger than the other? Well, that has to do with, take that, not that. That has to do with where x and y, where they're, what the joint density function ends up looking like. The one that we did first, we were in the lower left part of the plot, and so that hardly has any density there. So when we integrate over that, we get a really small number. The second one was in the lower right, and that has a little bit more density associated with it. So that's why we get a larger probability. You would expect that if we integrated something like, or if we found the probability that x is bigger than 0.5 and y is bigger than 0.5, that would put us in the upper right part of this plot. That should give us an even bigger number because there's so much density for this particular joint distribution in the upper right part of the plot. Hopefully that gives you a little bit of intuition. If not, we'll do a lot more practice with this, and you'll have a little bit more practice to do right away on your class prep quiz.